Good morning, ladies and gentlemen. It's Mr. Parkin again, bringing you another week of physical science. Let's just hop right into it. Last week, we talked about motion. We talked about the key terminology, important formulas that you would need to know, like speed and velocity, acceleration. And then we just talked a little bit on how to set up the graphs. Let's just talk about our standard that we're reviewing again real quick. We started this last week. Today's going to be the last day of the standard. Analyze and interpret data for 1 and 2 dimensional motion and apply those concepts of distance, displacement, speed, velocity, and acceleration, putting them into graphs or other conceptual models. So last week, we talked about these key terms. So we talked about motion. Motion is just when something has a change in position, all right, just a change in position. Position is where you are compared to an origin. So we talked about I would be at this tile right here, and then after the motion, I'd be 2, 4 tiles to your right, my left. That's position. Speed. It's just a calculation of how fast something is going. So we talked about speed equals distance over time. Speed equals distance over time. So that's just a calculation of how fast something is going. Real quick, if we can take this little demo and we can try to calculate speed by ourselves real quick. I'm a very clumsy person, so yes, I want to put some eye protection on in case this backfires on me. So basically what this is going to be doing is this little launcher is going to be launching this steel ball across the table, and it's going to stop right here. So the distance from the starting point to the end point is exactly 1.5 meters. All right, we got a meter stick, and I measured that this morning. So there's different settings on here. So each setting will launch it faster. We're just going to do the first setting for simplicity purposes. So right now we have our distance equals 1.5 meters. All right. I'm going to take my timer, and I'm just going to launch. I'm going to take the time of how long it takes to get to this point, okay? On the mark, get set, and go. All right, that took 1.37 seconds. So our distance is 1.5, and our time equals 1.37 seconds. So now all we're going to do to find the speed of the ball, so again, remember from last week, that's the average speed of that ball. To find the average speed of that ball, you're just going to plug these into that formula. So our distance is 1.5 divided by the time, which is 1.37. Always put your units. And then we're going to go to our fancy calculators, right? Our fancy calculators. So if we do 1.5 divided by 1.37, we get 1.09 meters per second. Or for simplicity purposes, you can go 1.1 meters per second. So that was speed. The difference in speed and velocity is velocity has direction. So if you wanted to say the velocity of that ball, you would just say it's 1.09 meters per second to your right. That's it. The next thing we talked about was acceleration. Acceleration is just the change in velocity over a certain time. So since it's the change in velocity, you've got to remember acceleration also has direction. So again, It's the change in velocity over a certain amount of time. The change in velocity can be written final velocity minus initial velocity, and then over time. So what that means is if you go from 0 seconds to 60 seconds in 3.5 seconds, remember that car from last week? You would have 0 to 60, so 60 minus 0, that's a total of 60 seconds, divided by your time, which is 3.5. So 60 divided by 3.5 meters per second over seconds. You want to make sure that you keep your units because you can't have an answer without units. Remember from last week. So you take 60 divided by 3.5, and the average acceleration of that vehicle would be 17.1 meters per second squared. All right. So we're still reviewing from last week, just in case you weren't here. Independent variable, dependent variable, and slope. Now the best way that I can review those is to pick up where we left off last week. So last week I left you with a task. Your task was to take this chart right here. Remember, we had Maddie and Rhett do an experiment about how fast they could ride their bicycle. The best thing that I can do is just put it up for you. This is what your graph should look like. You should have done that graph over the week, sometime in those 7 days. So remember, our time will be on the bottom. Our time is our independent variable. Our independent variable always goes on the x-axis, or the horizontal axis. All right, and then we have our distance. That is our dependent variable. Our dependent variable always goes on the y-axis or the vertical axis. So the way we're going to graph this is you just take one of them. Okay, so since Rhett was first, I'm going to take Rhett first and I'm going to graph him. So at 5 seconds, he was at 10 meters. So I just took my red marker and I put a dot right here at where these 2 points meet. At 10 seconds, he was at 20. So I just put a dot there. So when I got all my dots, I connected them. It has a really pretty graph about the distance and time that Rhett traveled. And then Maddie, I did the same thing. At 5 seconds, she was at 10 meters. At 10 seconds, she was at 20 meters, 15, 30, all the way. She finished in 30 seconds. See, it says it right on your chart. And then Rhett finished in 35 seconds. So who rode their bicycle the fastest average speed? Well, of course, Maddie rode her bicycle the fastest average speed because she finished quicker, right? So I don't think we even got to slope last week. Slope, if you've even covered slope in math before, slope, there's a formula for that. You can say rise over run, or you can say it's your y over your x. Rise over run, or your y over your x. So in a distance versus time graph, we can actually discover who had the fastest average speed. And the way you want to do that is you take the furthest distance either of them traveled and the total time that it took them to travel. So with Maddie, Maddie traveled a total of 60 meters, but she traveled it in 30 seconds. So we can take that slope and we can find the speed. So Maddie's speed will be 60 divided by 30. 60 meters divided by 30 seconds. If you take a calculator or if you do it in your head, 60 divided by 30 is 2. So Maddie's average speed was 2 meters per second. Okay. Now Rhett, he traveled 60 meters as well. However, he traveled that in 35 seconds. Now, 60 divided by 35 is 1.7. So Maddie in 2 meters per second and Rhett 1.7 meters per second. So right here we can see plain as day that Maddie had a faster average speed. All right? So that's what slope does for us. Now I want to get into slope just a little bit more. So we have our distance time graphs. There's 3 types of slopes you can have. You can have a constant slope. You see it stays the same the entire time. In your distance versus time graph, your slope shows speed. In your distance versus time graph, your slope shows speed. So if you have this type of slope, you have a constant speed. If you have a slope that increases, let's say like this, what is that speed doing, you think? Well, it's obviously increasing. So that shows an increase in speed. And then you can have a slope that decreases. So if we have an increase constant, this would be a decrease. So the slope of your distance time graph will give you the average speed. I'm going to say the average speed. Okay, it will give you the average speed. There's a difference in average speed and instantaneous speed. Remember from last week. So the average speed is the total distance that you go divided by the total time it takes you to get there. Instantaneous speed would be driving down the road looking at that speedometer. Now there is a way to get the instantaneous speed from a graph. However, that's going to be something you learn in physics when you get to physics, okay? So the velocity, I'm going to say velocity or speed time graph also has 3 types of slopes. So if you take meters per second and then you divide by seconds, remember that gives us meters per second squared. That is your units for acceleration. So the slope of a velocity time graph will give you the average acceleration. Give you the average acceleration. Remember the total time versus the overall velocity, okay? So that will give us that will give us basically a constant acceleration. A constant acceleration. So let's say that's 5 and that's 10 again. That'll be 2 meters per second squared. That's 10 and that's 22 meters per second squared. It's increasing by the same increments each time. All right? So if you have a slope like this, that will be an increase. And then if you have a decreasing slope, that'll be a decrease. So these are the 2 most important ones, distance and time. The slope gives you the speed. Velocity and time, the slope gives you the acceleration. I'm going to give you about 15 seconds to write that down if you can, or to implant that into your memory so that you do not forget it, okay? Acceleration time graph, that slope will give you something called the jerk. Now that's just it's how acceleration increases or decreases over time. It's called the jerk. That'll give you meters per second cubed. You don't have to worry about that in physical science, but I just wanted to mention it because these are your 3 types of graphs, and I didn't want to leave you hanging by talking about 2 and not 3. But you're still going to have the same types of slopes. That'll give you constant, that'll give you an increase, and that'll give you a decrease, okay? So what we want to talk about now is scientific models. A scientific model is a physical, mathematical, or conceptual representation of a system of ideas. All right? It's a way to show how something works in nature. So one way that we can do that is by graphical models. Well, guess what we started last week and we've been doing? This is a graphical model. Graphical models can be super, super, super helpful. It can tell you how far something has gone in a particular set of time. It breaks it down. So if I wanted to know how fast I was going at this distance, how fast I was going at this distance, it can show me all of that, okay? You use a graph to determine the relationship between your 2 variables. So your 2 variables, again, are your independent variable and your dependent variable. The independent variable is something that doesn't change in the experiment. So we can't change time. You start that timer and time is going to go on whether we like it or not. You can't say, okay, freeze time, and then everything in the world freezes. It doesn't work like that. So time is going to be your independent variable. The independent variable is the variable that does not change, that you cannot change in the experiment. Now, I say we can't change it. We can't say time freeze and it freezes. But what we can do is we can say, hey, I want to add more time to this. I can say, how far will it take, how far can they travel in 60 seconds? Or how far can they travel in 10 seconds? Just wanted to clear that up a minute. So you can say, instead of doing 60 seconds, I want to go 120 seconds. The dependent variable is what changes due to a change in the independent variable. So if I want to ride 60 seconds, don't you think that they're going to travel a little bit further than 60 meters? Yeah. If this trend continues, Maddie will probably travel 120 meters if she continues at 2 meters per second. All right, so it's just showing you how this independent variable, that the variable that you change in an experiment, relates to the dependent variable. The dependent variable is what changes due to the independent variable, okay? I'm going to say this one last time. The independent variable is the variable that you change during the experiment. Remember, you can't say freeze time. That's not how it works. You can add more time or take time away. And the dependent variable is what responds to changes in independent variable. All right? Moving on to conceptual models. A conceptual model is a representation of a system that uses concepts and ideas to show the relationship between 2 variables. So this can simply be a drawing or a picture, or this can be toys and models. So this first conceptual model that you see is a poster by NASA. NASA, great place. Thank you, NASA. This shows that there are planets rotating around the sun. Everyone knows that, right? Planets rotate around the sun. But imagine living in the day where you thought everything rotated around the Earth. And then this guy named Copernicus comes and has a model of these planets rotating around the sun, people thought he was nuts. But that's how it works. So here's another conceptual model. It's a model of the Earth being flat and a ship falling off the Earth. Do you know that people used to think the Earth were flat and that ships just fell off the side of the Earth if they go too far? Here's another conceptual model. It shows types of projectiles. Types of projectiles. All right, this ping pong ball just flew down to the table. Or I can throw that ping pong ball and you saw it made an arc shape. So one fell straight down and one made an arc shape. That's what we're going to finish up with today. It's 2D motion. 2D motion, here's another representation of that. 2D motion has a few things that you need to know. Vectors. A vector is a variable that gives direction and magnitude. So, if I wanted to draw a vector of that steel marble rolling across the table, I would have that little marble and then an arrow that said 1.09 meters per second. That showed what direction that it was traveling and the magnitude of speed, direction and speed. That's a vector. Gravity. Gravity is the pulling force that is created between two objects. In this case, it's the massive Earth and us, or those balls. So here is your object, and then gravity pulls down to Earth at an acceleration of 9.81 meters per second squared. Now, you need to know this. Acceleration due to gravity is 9.81 meters per second squared. So that means if I want to take, let's say, a tennis ball and drop it, but I'm climbing up to a cliff. I'm climbing up to a cliff. Now don't get jealous of my mad, awesome artistic abilities, okay? I'm going to drop this ball straight down. After 1 second, it'll be traveling at 9.81 meters per second, okay? After 2 seconds, it'll be traveling at 19.62 meters per second. After 3 seconds, it'll be traveling at 29.43 meters per second. Do you see the trend here? For every second it travels, it gets faster by 9.81 meters per second. Now let's say we threw something up in the air at its highest point. So if I throw something up in the air, it has to come back down. At its highest point, it is 0 meters per second. All right? The only force acting on this is gravity. That means it's in free fall. Remember, free fall is when there's only gravity acting upon the object. Only gravity. So this is two-dimensional motion. It's also called projectile motion. It's when objects move horizontally and vertically at the same time. So what you need to know about this is it has horizontal direction and it also has vertical direction. So just to wrap it up and review, we went over motion. We went over one-dimensional motion, which just has motion in one dimension, and we went over two-dimensional motion. I want you to make sure you have a good grasp on speed, a good grasp on acceleration. I want you to know how to do those graphs. Know that your slopes of a distance versus time graph is speed, and your slope of a speed versus time graph is acceleration. I'll see y'all next week. Y'all have a great day.